Now let's talk about hydrostatics. Hydrostatics means hydro is water and statics, not moving. So we're going to talk about situations where we have basically fluids at rest. Now, before we begin, let's remember there are three states of matter: solid, liquid, and gas. And there is a fourth state called plasma that we don't really cover in this class. Now, a solid has a definite shape and a definite volume. So my cube is a solid, its shape stays the same, and its volume doesn't change. A liquid takes the shape of its container, but it has a definite volume. So if you have that much water, it doesn't matter what your container looks like, it'll have the same volume. A gas, however, not only takes the shape of its container, it takes the volume of its container. So these may have the same number of molecules, but for a gas, they will have different volumes and different shapes. Now let's look at density. Density is a concept we really need to understand when we do fluids. Density is defined to be the total mass divided by the volume. And this right here is rho, R-H-O. It's kind of like a squiggly P. The units we use for density are kilograms, meters cubed. So whenever we're doing anything in this class, make sure we convert it to kilograms meter cubed. Now you will see this equation written in a number of ways. Sometimes you'll see that the total mass is the density times the volume. You may even see the volume is the mass divided by the density. Just know what you're looking at. This is the actual definition. Now let's talk about fluids. What is a fluid? By definition, a fluid is something that flows. It is also, F-L-O-W-S, it is also any material that cannot handle a shear stress. So I have a container, and if I apply a shear stress to it, the fluid becomes distorted. And a solid, if I were to take a long metal bar and I apply a shear to it, then it may deform a little bit, but it will recover. However, fluids cannot recover. Fluids include gases and liquids. So fluids flow. They take the shape of their containers. One fluid I especially like is sand. Sand is a fluid because it flows. You can pour it. It takes the shape of its container, and if you apply a shear stress, it changes its shape permanently. Now, why are fluids so useful in physics? Well, first of all, remember, our fluids are incompressible. Incompressible means that the density does not change. Now, if I do work on this fluid, then in a sealed container, then I can treat this just like an object. The pressure I apply, remember pressure is force per unit area. The pressure I apply, we say it's transmitted throughout the entire liquid instantaneously, and it is not diminished. So these are idealized fluids. Let's talk about what pressure is. I just told you pressure was force per unit area. And in fluids, it's an essential concept. The units we use for pressure are newtons, meters squared. So make sure you convert everything to newtons and meters squared. We use Pascals to denote newtons meters per square. So you can also use Pascals as your units. Let's look at an example. Suppose I have a waterbed that is 2 meters on one side and 30 centimeters deep. So I'm going to draw my waterbed here. It's 2 meters on one side, and then, okay, my student makes fun of my drawings. It is 30 centimeters deep. Find the weight and density of, if the density is 1,000 kilograms per meter cubed. Now we're going to assume this is a square waterbed. Let's see. The volume is a cross-sectional area times the depth. So the area is 2 meters times 2 meters times, and I'm going to convert this 30 centimeters to meters, or 1.2, meters cubed. So I have a volume of 1.2 meters cubed of my little waterbed. B, find the pressure that the waterbed exerts on the floor. Assume the entire lower surface makes contact with the floor. Well, let's see. I know density is mass per unit volume. So I need the mass. The mass is going to be the volume of water times the density. And let's see. The volume I just found is 1.2 meters cubed. The density of water is 1,000 kilograms meters cubed. You can memorize that. Or it has a mass of 1,200 kilograms. What is the force that this applies? If I wanted to find the force, well, the force is just going to be the weight of the water, which is 1,200 kilograms times 9.8, or about 11,760 newtons. But we ask for the pressure. Pressure is force per unit area. So this is 11,760 newtons divided by my area of 1.2 meters cubed, or about 2,940 Newton meters squared, or pascals. Now, let's talk about hydrostatic pressure. Suppose I have a fluid that is at rest. We're going to call this a this is a static situation. The pressure we're going to talk about is hydrostatic. Now, 2 important points. The fluid exerts pressure in all directions. So this is not an up, down, left, right situation. And a fluid always exerts a pressure perpendicular to the surface. So notice that the arrows on top are smaller than the arrows on the bottom. This is because pressure is affected by depth. So objects at the bottom have more pressure on them than objects at the top. Let's look at how this works. Suppose I have a situation where I have an object that is sitting just at the top of a fluid. We can call this water. Now I'm going to get rid of this real quick because that's kind of cheating a little bit. Well, it doesn't want to go away. Alright. Suppose we see that it's submerged so that it's just touching the atmosphere. Let's draw a free body diagram of what we have going on here. Everyone knows first force you always draw on a free body diagram is the weight. So this is the weight of the object. So this is the mass of my object times g. And I also know there's a force pushing down on it, due to the atmosphere. So I'm going to write that down here. This is a force of the atmosphere. And we know that there is a force pushing up. So this is, I'm going to call this a buoyant force. Now, let me go into what happens to these forces as we go further down. Remember, pressure is force per unit area. So if we solve for force, let's see what we have. The force pushing down is our initial force, our initial pressure, our outside pressure, times the area. All right. And what else is pointing down? mg. Now what forces do we have pointing up? This is just the pressure right down here times the same cross-sectional area, the area at the second point. Well, remember, density is mass per unit volume. So mass is the volume times the density. So let me rearrange this. So I have the initial pressure of the atmosphere times A plus rho Vg has to equal the pressure at the bottom times that area. Now what's another formula? Volume is area times width, and in this case that width is going to be h. So let me plug that in. Alright, so I'm going to reverse them. P times A is P naught A plus rho A Hg. So what do I wind up with when I cross out my areas? I find the pressure at this depth right down here is equal to the atmospheric pressure plus rho GH, where rho GH is the added weight due to the displacement of the liquid. Now, let's look at this. This is very important. If we look at this, we are going to ask you for a variety of things. I'm going to ask you for the absolute pressure. That is P. That's the pressure you feel at the bottom. Whoa, not a very good diagram. P naught is the initial pressure. It may or may not be the atmospheric pressure. In the example before it was. And rho GH is the added pressure because you're beneath the surface of a fluid. The other thing I'm going to ask you for is gauge pressure. Gauge pressure is simply the change in pressure due to an object being submerged. So this is what the gauge would read. Let's look at an example. Suppose I have an ocean. I'm at the ocean and we're at a depth of 1,000 meters. I assume the density of water is 1,000 kilogram meters squared. That's H. And 1 atmosphere is 1.01 times 10 to the 5th pascals. If I want the absolute pressure, that's P is P naught plus rho GH. So this is 1 times 10 to the 5th plus the density of water is 1,000. G is 9.8. And I'm at a depth of 1,000 meters. So I get an absolute pressure of 9.9 times 10 to the 6 pascals. Now if I want the total force exerted outside of a window of 30 centimeters diameter in a circular submarine at this depth, let's see, pressure is force per unit area. So the force it's going to feel is the pressure at that depth times the area of the window. So it's the pressure times the area. Now the area is pi r squared. So let's see. This is the pressure is 9.9 times 10 to the 5th pascals times pi, and the area here is 0.15 meters. Remember, you always have to convert this to meters time, so you can get the correct units here. And I come up with, let me square this, 6.36 times 10 to, let me count my decimals, 1, 2, 3, 4, 5, 6, 7, 8 newtons. Now, let's continue on. What if we have a closed system, like like your brakes? Remember, the pressure is the same everywhere. So the pressure at any one point inside your brakes is equal to the pressure at any other point. Now, because this is true, if you say apply, so let's do this, if you apply a force at any one point, there will be another force at any other point. Let's look what this looks like. Pressure is force per unit area. So P1 is F1 divided by A1, and P2 is F2 divided by A2. Now, we take advantage of this fact all the time. This is called Pascal's principle. So if I know the force and the area of both, say in a pneumatic lift, I know I'm applying a particular force to a particular area, I can tell you what force it will be able to lift another object. Let's look at Pascal's principle with a bottle. Suppose I have an initial area of 5 centimeters squared, and I apply 10 newtons to the top. If the bottom has an area of 500 centimeters squared, what force is being felt here at the bottom? Well, F1 divided by A1 has to equal F2 divided by A2. So the force at the bottom is going to be F1 divided by A1 times A2. So the force I'm applying is 10 newtons. I'll multiply it this way because I like it this way. A2 is 500 centimeters squared, and A1 is 5 centimeters squared. And now we don't have to convert this to meters because they're both in centimeters squared. So F2 is 1,000 newtons. You see how using Pascal's principle, we can take a small force and convert it to a very large force. Another example is your brakes. Now, this is very, very important when you're driving your car, because you have the force of the brake cylinder. Here's your brake shoe, and then there's friction of the brake pedal against the drum, and then this is the force of the fluid by the brake pedal on the mechanism. Now, you really do not want to have to apply enough force with your feet to decrease your car's motion. So, the force on the brake pedal, which is what you're pushing on, divided by the area of the brake pedal, has to equal the force of the shoe, the brake shoe, divided by the area of the brake shoe or the brake pad. Now let's look at buoyancy. Everyone's been waiting for this one. Buoyancy is an essential concept. When I have an object that is submerged or partially submerged, there's going to be an Fg pointing down and then some sort of buoyant force pointing up. Now, if the object is totally submerged, the volume of water displaced is going to equal the volume of the object. Archimedes came up with a fascinating theory or principle. An object is buoyed up by a force equal to the weight of the fluid displaced. So, we see that this object out of water weighs 7 pounds. When we put it in water, it weighs only 4 pounds. So there is a difference of 3 pounds between its air weight and its fluid weight, or when it's displaced in a fluid. And that is 3 pounds of water. So what that tells us is there is a weight going down equal to the weight of the object, but then a buoyant force of 3 pounds pulling your object back up, or pushing your water back up. This is one of the reasons we tend to feel less, you have less weight in water, you feel lighter in water than you do in air. So, Archimedes' principle says the buoyant force is equal to the weight of the fluid displaced. Let's rearrange this, since I know mass is fluid, is density times volume. The mass then is density times volume times g. And we know that the volume of the object must equal the volume of the fluid. Let's do an example. Suppose a bargain hunter purchases gold, a gold crown at a flea market. After she gets home, she hangs it from a scale and finds it's 7.84 newtons. And then she weighs it when it's in water, and the scale reads 6.86 newtons. Is it made of gold if the density of gold is 19.3 times 10 to the third kilogram meters cubed? Well, let's see. Inside, here's my crown. It has Fg going down and Fb going up. And its acceleration is 0. We have a static situation. So, we have, this is underwater. Out of water, it has Fg, and then its tension. So, I know the object weighs 7.84 newtons. So, the tension, or the weight of the object in air, minus the force felt in water, has to equal my buoyant force. So, what do I get? Fb is equal to 7.84 newtons minus 6.86 newtons, or 0.98 newtons. Now, the buoyant force is equal to rho, density of the fluid, volume of the fluid, times g. So the volume of the fluid is 0.001 meters cubed, and this is the same as the volume of the object. So I get a mass of 0.80 kilograms. Let's look at this. The density of the object is the mass of the object divided by the volume of the object, and the mass is 0.8 divided by the volume, which is 0.0001, or 8,000 kilograms meter cubed. Well, if the density of gold is 19,300, clearly her crown was not made of gold.